Rockets launch at a high rate of velocity, but they need to come down gently and safely. Recovery systems account for more than half the flight time, but they get much less attention than the launch. Remember that certification requires that you recover your rocket in flyable condition, and the competition requires that you ensure a safe landing. First Nations Launch welcomes you to Recovery Systems. A rocket recovery system is any method that returns the rocket safely to the ground. The most common and the one relied on by First Nations Launch is parachute recovery. But it is worth knowing that there are several other methods, including parawing, helicopter, and rocket glider recovery. Recovery systems consist of several parts that work together to reduce the airspeed of the rocket, so it can be recovered and flown again. Tripoli Rocketry Association safety codes require every rocket to have a recovery system. High-powered rockets typically have either single-event recovery or dual-event recovery. A typical single-event recovery system ejects a parachute at apogee, the highest point of the rocket flight. This can most commonly be achieved by using a delay grain to ignite the motor ejection charge. At launch ignition, the propellant and a delay grain both begin to burn. The delay grain burns slowly. After the main propellant is exhausted, the delay grain continues to burn and ejects smoke, making it easier to track the rocket. The rocket continues gaining altitude as its inertia slowly dissipates. Ideally, the delay grain is timed to burn through and ignite the ejection charge for deployment just after the rocket reaches apogee. If the delay ignites too early, it may have to fight the drag against the nose cone and may fail. Likewise, if the delay runs too long, the rocket may reach apogee and begin descent acceleration. For example, ejecting a parachute while moving at 300 feet per second puts excessive strain on the parachute, shock cords, attachment points, and airframe. So the recovery system must be able to handle forces 40 to 60 times the rocket's total weight. You also need to select your parachute size, balancing between descent velocity and drift range. Given the accurate weight of your rocket, you will want a parachute that slows descent to approximately 20 feet per second. In this example, for a 10-pound rocket to reduce descent speed to 20 feet per second, you would want a parachute of at least 72 inches in diameter. You can use RockSim to run several simulations and determine both the optimal delay charge time for various motors and the optimal parachute size to handle variations in weather conditions. Then you will have to actually build your recovery system and check its true weight. The recovery system is connected by a recovery harness, generally a long length of tubular nylon that links all of the separated rocket components. Each end of the recovery harness attaches to your rocket at anchor points, typically forged eye bolts or U-bolts, securely mounted in bolt plates on the booster section and the avionics bay. The descent control device, in this case a parachute, consists of a canopy made of several ripstop nylon cloth panels called gores, connected to shroud lines attached to the harness with a still-quick link. The main parachute is generally attached to a loop in the shock cord tied just below the avionics bay. The length of your recovery harness should be roughly 3 to 5 times the length of your rocket. In other words, long enough to allow the sections to eject and begin free fall without pulling the recovery harness taut. And then they should be offset enough to float down without banging into each other. Once again, feel free to calculate the maximum load from acceleration, following the deployment charge, and check it against the braking strength of your harness. And then, if you really want to test it, hang it in the wind and see if your rocket components hit. The parachute and shroud lines need to be folded for clean deployment. There are several methods for folding. The way that you fold your parachute can control the speed with which the chute opens. For rapid deployment, shock cords should be openly S-coiled or crochet looped to save space. But the greater forces involved in high-powered flight benefit from slower deployment, so the parachute may also be wrapped loosely with the shock cord, crisscross, or candy cane style. Then the recovery system should be heat protected before placing it into the airframe. Flame-proof Nomex or Kevlar cloth can be used to burrito wrap the recovery device. You can also insulate the recovery system using flame-resistant cellulose insulation wadding, called dog barf by real Rocketeers. Dog barf is simply the cheapest flame-resistant material you can get to protect your recovery system from hot ejection gases. A good insulating layer of loose dog barf, as much as comfortably fits, will dampen any direct flame contact from the ejection charge. Now that you have a complete recovery system, you can weigh and calculate the size of the ejection charge required to deploy it. The sustainer section of your rocket will be attached with shear pins. 3 nylon 256 shear pins require about 180 pounds of force to break. So how much black powder is required to break the shear pins and fully deploy your recovery system? Remember that the ejection charge will be located at the front bulk plate of the motor mount system, behind the flame-resistant insulation and packed recovery system, along with the forward section of the rocket, including the avionics bay, sustainer section of the airframe, and the nose cone. All of these components should be weighed and figured into your calculations. And once you have the confidence in the mathematical prediction, it is time to run physical ground tests. Make sure to observe school safety practices for conducting experiments with pyrotechnics. Some colleges may not allow pyrotechnics, and you must abide by their rules. In such cases, you can conduct force tests using alternative methods like pneumatic CO2 or air charges. But here, we'll describe how to test the same materials you will be using at the launch. You should also test your altimeter, but we'll save that explanation for a bit later. High-powered motors have delay grains and black powder ejection charges housed in the motor casing. But you won't have access to that, so you will need to mount a small ejection charge tube where the motor charge would be. You will also have to create a safe ignition control system to conduct your test. You will find this work is not only good science, but good practice for dual deployment systems later on. Your team safety officer should be looking out for any possible dangers, and you should document each step as you go. To model your motor ejection charge, mount a small piece of tubing in the center of your booster section bulk plate where the motor will be. Pour in a calculated and measured charge of black powder. Place an igniter into the black powder. Then use some dog barf to pack the black powder and igniter into the tube. Place some masking tape over the tube to hold the charge in place. This is one standard method of performing dual deployment systems. Mount the sustainer section, weighted and packed just as it will be in the launch with the proper shear pins. Once that is all in place, safely connect the ejection charge position yourself at a safe distance, and then ignite the ejection charge to test if it generates enough pressure to deploy your recovery system. Start with the minimum charge and then gradually increase the size of the charge until you have an effective deployment. Make sure to consider how drag and air pressure will affect your rocket separation. For example, this plot shows the trajectory of a rocket using a single event recovery system. The rocket completed power ascent and coasted under inertia to an apogee of 4,800 feet. It then deployed its recovery system, slowing the descent rate to 20 feet per second. It took approximately 4 minutes for the flight. Dual event recovery systems have one event at apogee deploying a drogue chute or streamer and a second main chute deployment at much lower altitude, but no less than 300 feet, triggered by an altimeter. The advantage of this technique is that your rocket descends much faster from apogee and lands much closer to the launch pad. As another example, the plot shows the trajectory of a rocket using a dual event recovery system. This rocket reached the same apogee of 4,800 feet. It then deployed a drogue that slowed the descent to 90 feet per second. At 900 feet, the altimeter deployed with the main parachute, slowing the descent rate to 20 feet per second. It takes approximately 1 minute and 40 seconds for the flight. A rocket equipped with the dual event recovery system generally mounts the first stage of recovery to be deployed by the motor ejection charge and places the second stage, or main deployment, forward of the avionics bay. Placing the heavier recovery device forward pulls forward the rocket's center of gravity and improves stability. The avionics bay is generally between the two stages of the recovery system. This allows the avionics bay to directly trigger the main ejection charges, which are mounted on the avionics bay's forward bulk plate. Needless to say, if you already went through testing your single deployment charges, you are well prepared to configure and test the dual deployment system. However, there are a couple of important differences. Whereas the single deployment uses the very reliable launch motor as the ignition for the delay and ejection charge, the second deployment needs to be initiated during flight and from a separate location in the rocket. Since the main deployment will be triggered by the altimeter, proper fail-safe planning calls for redundant altimeters designed to handle dual deployment with multiple main deployment charges. One altimeter will trigger at apogee, and the backup altimeter will trigger at apogee plus 2 seconds. This will ensure that all of the charges do not ignite at once and overpressurize the deployment. This time, you will need to test both the altimeters and the ejection charges. The altimeters operate by measuring changes in air pressure. Many schools have vacuum chambers that you can use to confirm your altimeter functions by triggering an LED light with a switch. If you don't have access to a vacuum chamber, you can try alternative methods, like creating a temporary vacuum chamber by using an air pump or even a vacuum cleaner. When ground testing the ejection charges for your secondary recovery system, you will need to consider that you will be using redundant systems. Just as with single deployment, each ejection charge needs to fully deploy your recovery system. But you will want to make sure that your combined charges do not fire simultaneously. So your redundant altimeters will need to be offset in their trigger timing by 2 seconds. This will give you a safe margin. Perhaps the greatest challenge involving dual deployment is having confidence in your electronics. So, one last tip. Until you are confident in your secondary deployment, consider using a larger drogue than necessary. If for some reason the electronics fail and the main parachute does not deploy, your rocket will not be a total loss. And if your dual deployment succeeds, it will just mean walking a bit further to recover your safely landed rocket. Hopefully by the time you get around to dual deployment testing, you will be enough of a veteran to decide how to best handle it. Together, we'll make sure what goes up in First Nations launch comes down safely.
The guidelines in this video are provided by Tripoli Wisconsin Rocketry Association, host of the First Nations Launch Program at Richard Long State Recreation Area. When launching locally, please check with your local TRA prefecture or NAR chapter.